Okay, the second lesson then of mechanics year 12, constant acceleration, is velocity time graphs. So we just did displacement time graphs. Okay, velocity time graphs, well, instead of displacement, we've got velocity here each time, which is in meters per second here. Now, you can see some obvious problems. So first of all, you need to know which one you're dealing with. Please make sure that you read the axes carefully, that you read the situation carefully, because you do fundamentally different things with the displacement time graph and a velocity time graph. The displacement time we did before, looking at this line here, told us about velocity. Well, looking at the line on a velocity time graph is going to tell you about something else. As always, we try and follow the journey of what's going on first. Velocity. The thing has no velocity, and it has no velocity as time goes on. In other words, it's not moving. The object's stationary. Here, the object has a velocity. That's kind of like a speed, remember? So it's moving, and that movement carries on and carries on and carries on. So you're moving, you have a speed, and you keep having a speed, you keep having a speed, you keep having a speed, if you like. So the thing is moving, but it's moving in a constant way, constant velocity. How about this one here? So it starts with a velocity straight away, and as time goes on, this velocity is increasing and is increasing and increasing. In other words, it's accelerating. And this acceleration is constant. Think of the name of the chapter here, constant acceleration. And that's shown by the fact that it's a straight line. Okay, so what's going on here? Well, acceleration, here this was no speed, not accelerating, speed, not accelerating. I had some speed and it was accelerating more. Acceleration must be given by the gradient then. Okay, more formally, it's how velocity changes over time, or the rate. Rate is about time, or the rate of change of velocity. You might remember this from GCSE. Okay, sometimes at GCSE you had some sort of curved graph like this, and you had to draw on a tangent to estimate the acceleration by doing something like this. It's kind of the same thing. What you might not know, or might be less familiar, is that the area under a velocity time graph, so here that area is given by a rectangle, for example. Here it would be given by a trapezium. The area underneath gives you the distance. Okay, it's actually not the displacement, it's the distance. Sometimes they're the same thing, but it's a little bit tricky, and we'll come back to this idea later. In general, area, because area can only be a positive quantity, well, if you talk about all of the areas, that's your distance. So think about what an examiner would like to do. An examiner wants questions that link lots of things together. So velocity time graphs are perfect for this, because what the person can do is maybe they could do a part A question on acceleration and a part B question about distance or displacement, as we will see later. Let's have a look at a question then. So the question, I just realized I've still got my face mask on. I don't need that. The question is shown here. This is a velocity time graph. It looks like. Double check though. It could always be a speed time graph or something like that. You need to double check. So a velocity time graph, yes, illustrates the motion of a cyclist moving along a straight road for a period of 12 seconds. Okay, so 0 to 12, that's the journey. Tip for you mechanics, if you've used all of the information and you've checked it's all labeled and stuff, you can actually cross this off, so you know you don't need to come back to it. For the first 8 seconds, okay, for the first 8 seconds, she moves at a constant speed. Okay, so 6, 6, 6, 6, and so on and so on. Notice how they use the word speed there instead of velocity. Here they are the same thing, because we're going in one direction by the look of it. Well, that's labeled. I can get rid of that. She moves at a constant speed of 6. Yeah, that's already on the diagram. She then decelerates. So if you're decelerating, your velocity should go down. Yeah, that makes sense. So this one's going down. She then decelerates at a constant rate. That's why it's a straight line. Stopping after 4 seconds. 4. Okay. So what I'm doing there with how I'm circling the information and crossing it out and things is something that you want to do when you're doing a mechanics question as well. Okay. I also try and look at the words and look at the diagram, because sometimes you don't have the diagram, you've only got the words. So you need to check these. Find the displacement from the starting point of the cyclist after this 12-second period. So displacement. Well, let's try and sort of think about what's going on to start with. So this person is moving at a constant speed in a straight line, it said. So they're going like this, they're moving along, they're moving along, they're moving along, and then they sort of slow down and then they stop. Okay, so I want you to think about in this situation, is displacement any different from distance, or are they the same thing? Well, because it only travels in one direction and it doesn't go back and forth, they're the same thing. So this will be the same as sort of finding distance for this question. So we want the area under the graph. 6 times 8 for your rectangle, 4 times 6 over 2. You could do it that way, or you could do the area of trapezium, which is generally a bit faster. Okay, and you should be able to work that one out there. Work out the rate at which the cyclist decelerates. Well, rate is often something to do with time. The cyclist decelerates. So decelerates means the velocity is going down. So we're talking about this section here. So they go down by 6 over 4 seconds. So I could do that one there. Now, that's actually not a fully correct answer. So why is that not a correct answer? Because I've been told that they decelerate already, and I've got a negative. So this is like a double negative. The rate they decelerate is actually just 6 over 4, because that negative is already being taken into account by the question. So it should just be 1.5 meters per second squared. Okay, very common exam question now is an algebraic example. So here we go. A particle moves along a straight line. The particle accelerates uniformly from rest. So it's going to start at 0 by the sounds of it, to 8 seconds. What I'm going to do is I'm just going to read and see which kind of graph here. So sketch a velocity time. So let's try and follow it along. So it started from rest, a uniform way. So accelerates uniformly from rest to 8 seconds. So uniformly means we're dealing with a straight line. Constant acceleration, remember, is the name of the chapter. That's kind of why we're doing this. So that's 8 seconds. Once you've used the information, cross it out in t seconds. Okay, there's t, cross it out. The particle then travels at a constant velocity. Well, we know that means we've got one of these flat lines here. 8, yeah, 8 for 5t. Not until 5t, for 5t. So t plus another 5t, that's 6t then. The particle then decelerates, so we're going down uniformly. Okay, so we're going down in a straight line in a further 60 seconds. Okay, so this is what we're looking at then, 6t plus 40. Just check we've read everything. I think we've used all of that information. And that's actually our part A, isn't it? Sketch the graph. So there we go. Okay, key features. We wanted these values here at the bottom and the 8. That's what they're looking for. Find the value of t. Right. So we don't know what this t value is, but we've got a graph. So maybe we can link it to something else. Just above the question, look, the new information. Given that the total displacement of the particle is 600 meters, well, what part of the graph is that, the 600 meters? Well, again, we're only sort of traveling in a straight line here, no back and forth. So that displacement is the same as the distance. We're actually talking about this area under the graph that is equal to 600. So what you need to do is you need to tell me what it is in terms of t, and then you've got it as 600. Set those equal to each other. You should be able to do some problem solving and find that one there. So we do area of a trapezium is the quickest way. So this is our A value, this is our B value, this is our H value. A plus B, so A plus B over 2 times H. Let's write it down like that. A is going to be 5t. B is going to be t plus another 5t. That's 6t plus 40. So plus 6t plus 40 over 2, and we're multiplying the whole thing by 8. And remember, we've been told that it's 600 meters, so we need to set it equal. So we should get this one here and our value of t. You also, like, if you get a negative number there, think about why that would sort of cause alarm bells to ring. What is t? T is a time. Time can be positive only. So we've got a few more. Distance, speed, and time can only have positive values. Okay, displacement, velocity, acceleration have directions. Okay, and you will see positives and negatives with these. I'd like you to pause the video and have a go at, here we go, at part A and B. You can have a go at C for a challenge, but you can please ignore D for now. Clear diagram, reading through, ticking off the information is the way to answer this one. So I'm assuming you've had a go at that now. Your sketch should look a little bit like this. If you didn't get B because your diagram wasn't there, pause the video again, have a go. And once you've done that, have a look. So for B, the same sort of question, T should be 75. Is it always a trapezium like this? I suppose there could be some more bits and pieces. Okay, we could sort of add on. It's possible. Or sometimes you have to work backwards. But it's about understanding that the area is the distance. Okay, and the value there for C, a more difficult question. Okay, so that takes you to the end of the graphs. So we have displacement time graphs and we have velocity time graphs. In the next section, we're going to look at SUVAT equations. SUVAT, the S is for displacement, U and V are about speeds, A is for acceleration, T is for time. So these graphs here, they can be used to come up with some really, really useful formulae to describe things moving, essentially. And that's what we're going to have a look at in the next section.